We will now look at the solution of the third problem in the second Maple test. So this problem is about implementing the steepest descent method, which we can find the pseudocode for at the bottom of page 234 in the textbook. And we're going to test our implementation using the A and B matrices given, or the A and B vector, A matrix, B vector given below here. And we're going to use a maximum iteration count of 2000 for our testing. And once we're done, we can compare our computer solution against Z, which is a known solution. So since we're going to use matrices and vectors, it might be a good idea to include the linear algebra package. And it's always a good idea to do a restart. So let's do that too. And let's see. We need to implement the steepest descent method, so we would need a procedure. Let's call the procedure steepest descent. Oops. It's going to take the A matrix as input, the B vector, and a maximum iteration count. It's gonna default to 2000 here. Gonna do it like this, and then we're gonna apply it. To our test problem, like so. And then we're gonna compare computer solution against the known solution, like so. Okay, so for the implementation, just gonna dig into the book and pretty much convert pseudocode into an implementation. So just write the iteration loop. Once this is done, we're going to return the solution. So like this, and we need a local iteration counter. We need a local storing recurrent iterate. This is going to be a vector. And we also need to know how many components we have in our problem. So we could do, for instance, like this. Okay. In each iteration, gonna update the current iterate by subtracting the gradient, or a step of size t in the gradient direction. We need to compute the step size, and let's call this R for residual, because the gradient here is basically residual, so a bit nicer. Something like this. And we also need this step size t. We need to compute this. So let's see. According to the book, t should be something like this. Let's just sanity check this. Looks okay. Okay, let's see if it works. We have an error somewhere. It's probably here, missing 2, I think. Let's see if that worked. Okay, so we managed to get this one out, and we got the solution. It's quite a big tolerance down here, so we might worry that some error in our implementation. So let's try and crank up the number of iterations just to verify that this error would go down. Not much is going to happen here. We're going to do something more. Okay. Try and go the other way. Seems pretty independent of iteration count. So let's go back and look at the code a little bit. Okay, so looking at code looks pretty okay. So it might just be that the convergence rate of this method is too bad. So let's see if we somehow could get that as an output somehow. So let's try and record the convergence rate. Just add in an extra argument here, where we basically just gonna collect up how the residual changes, like so, and we need to let's call it something meaningful. Like so. Make a little plot. See if this works. Spilling out. Okay. So it seems like I swapped X and Y axis here. So do like this. It'll be a little bit easier to see what goes on. Okay, here we go. So what we can basically see here is that after 8 iterations or so, steepest descent is not really performing well any longer. Might as well just give up. So our implementation is actually correct. It's just that running for 2000 iterations is a bit insane, given that the method converts so poorly. That's it.